All right, half-life. Half-life is the time required for half of a compound, a reactant, to be consumed, right? And so for first order reactions, we have this law. Uh, the half-life equals ln2 over k. So if I know the rate constant, I can figure out the half-life. All right, so for this one, we have a k of 0.0025 seconds to the minus 1. So I can figure out ln2, that's 0.693, divide that by my half-life, and I get out of this 280. This is in seconds to minus 1, so I get seconds. So this is the half-life. What this means is if I start off with 4 molar solution, after 280 seconds, I'm going to have 2 molar. 280 seconds after that, I'm going to get 1 molar, etc. I can use this. Now, in class, we did a first order reaction that has a K equal to 25 seconds. So the K is bigger. That means that it is a faster reaction. And so when we figured out the half-life for that case, we ended up with a fact that that one had a half-life of 0.028 seconds, right? So a higher K means a faster reaction, means a shorter half-life. That means in that case, every 0.028 seconds, you get half as much. Okay, let's move on to video problem 11b. 11b says there's a first order reaction with a half-life of 125 seconds. If the initial concentration is 1.6 molar, what is the concentration after 375 seconds? All right, so what are we given? We're given an initial concentration. We're also given a half-life. And from that, we're asked to get to the concentration at 375 seconds. All right, so how am I going to do this? Well, I'm going to do this by first using this to find K. And once I find K, I can find the concentration. All right, so if half-life equals ln2 over K, then K equals ln2 over half-life. That's 0.693 over 125 seconds. So that's going to get me my my K value of 0.00555 seconds to the minus 1. Seeing that this is over seconds, this will be seconds to the minus 1. That is my value for K. Now that I know K, I can use the fact that this is first order, right? And so that is, seeing that it's first order, the ln of my concentration equals negative kT plus ln of my initial concentration, 1.6 molar. So I can now plug this in. I want to know it at 375 seconds. And then I'm going to add the ln of my initial 1.6 molar. And that's going to get me my result. All right, so multiplying 0.00555 times 375, that gets me 2.08. The natural log of 1.6 molar is 0.47. I'm going to add these two up, and that's going to get me negative 1.61. Now, here's the thing. That is not my answer. That's just my natural log. So now to actually find the concentration, I need to use this. All right, so let's go ahead and do that. So I just found that my ln of my concentration is negative 1.61. So if I want to know the concentration, what I have to do is I need to do e to that. Because e to the ln A gets me my concentration. So e to that, right? So in my calculator, which I do not have right next to me, but I am finding it, right? So 1.61, I go ahead, I do second function, and then this key right here, yours may vary, I get 0.1998 or 0.200. This is the concentration, so it's more. So that is my concentration after 375 seconds. Now notice, there's something else I could do. If I start off with 1.6 molar, the half-life's 125 seconds. So after 125 seconds, I'd end up with 0.8 molar. After 125 seconds more, I'd end up with 0.4 molar. After 125 seconds more, I'd end up with 0.2 molar. Okay? That's how half-lives work. Well, notice 375 is 125 plus 125 plus 125, or 375 seconds, right? So I get the same answer. This way, I have to do the sequential half-lives. Here, I'm using the calculation to do it. Sometimes it won't be easy. This one just happens to be 3 times the half-life. Okay, so with that, that is half-lives. Let's go ahead and put that on the screen, and that's how we did the calculation. All right, next time, I'll talk to you about mechanisms. Have a good day.